DC-DC converters, isolated, unregulated, like these ones here. 5 volts to 5 volts, 200 milliamps maximum output, so 1 watt. And I have one here in my breadboard. Yeah, the whole setup here I already had it on the bench because I made a video about DC-DC boost converter from Banggood, card link. And yeah, this is an addition. This is the exact input voltage the little bugger gets. That's its output voltage, which is obviously not 5 volts. And that's the load current. And yeah, here is the first pitfall using these thingies. But first things first. So what is an isolated, unregulated DC-DC converter? I've drawn the symbol up here, and when would you typically use it? Well, simple explanation is such a converter is basically a transformer for DC. So instead of, if you have AC, taking an AC transformer to transform a voltage and have completely galvanic isolation between two sides, you can use these thingies to transform a given input voltage, DC input voltage, into a given DC output voltage. In fact, internally, they are obviously working with switch mode and a little transformer for higher frequencies. So yeah, it boils down, it's a transformer for a DC. And the typical application here, yeah, just out of my head, you have somewhere an, yeah, let's say an MCU, everything works fine, yeah, 5 volt supply, you have, yeah, it's there. And now you want to do something with that MCU in a 230 volt or 400 volt mains AC environment, yeah. And of course, you have here a keypad and some other user input stuff connected to the MCU. So yeah, it's a bit yeah, uncomfortable. And there your isolated DC-DC converter comes in. But yeah, standalone, it makes absolutely no sense. You need other parts. For example, there is something called isolation amplifier. Yeah, you put an analog signal in and an analog signal comes out. And there's isolation between the two ends. Which means, of course, for that thing to work, it needs on one side a power supply, which is, yeah, no problem. Yeah, we already have a 5 volt rail here. But it also needs to, yeah, generate the analog output, a power supply on the other side. Yeah, the other way around works, of course, too. And there are things like, they are called digital isolators with several channels, bidirectional, whatnot. Same problem, yeah. On the one side you have your power supply, it's already there, but you need a second power supply on the other side. And here comes the unregulated, isolated DC-DC converter in. Because you have already here a regulated 5 volt rail, usually in your application, or 12 volt rail, or whatever. And yeah, so that thing doesn't need to regulate that much, does it? Or to stabilize some battery voltage that you get, or some voltage from a transformer. No, it just has to get a given stable voltage, yeah, isolated to its other side to supply, yeah, all your isolated elements and what else you have on this side, the high voltage side. So, and that leads directly to the second point. When wouldn't you use an unregulated, isolated DC-DC converter? And the answer to that is much simpler. Forget about that for the moment. Yeah, typical, yeah, you have mains AC, you have your transformer, you have your bridge rectifier, you have your filter capacitor, and then you have your V plus rail somewhere and your ground. And now you remember, I also need a negative rail. So, would you use an isolated, unregulated DC-DC converter? You could. Yeah, well, not really. There are two problems. I mean, you can connect that thing in this way. Yeah, remember, this is galvanically isolated from here, gives out a voltage. So if we connect our plus to our ground rail and the minus output to our negative rail, yeah, it should work. Two problems. The first is, if it says unregulated, it means unregulated. And the input voltage range of the unregulated sort is normally very narrowly specified. So yeah, my rail here is unregulated, and yeah, so what comes out here is also unregulated. That's okay, but you might destroy the poor little thing when you exceed the narrow band of input voltage it expects. And the second reason not to use it in such an application is you spend dollars for a feature that is the isolated, which you don't need. I mean, basic thumb of rules, if you put that into your circuit and you find any connection between one of the out pins and one of the in pins, like yeah, here over ground, you wasted the money for the isolated feature. Okay, let's get back to the initial problem I saw. So right off the bat, I said, okay, our input voltage is 5 volt. We have no loads in milliamps, and the output voltage is 6.3 volts. And this is supposed to be a 5 volts to 5 volts isolated, etc., unregulated converter. So what's going on here? That's from the very start of the data sheet after the marketing blah blah. And you see here is something called minimum load is 0%. So what's going on? Well, it's the node 3, which states operation below 10% load will not harm the converter, but specifications may not be met. That's a nice sentence, isn't it? Basically, it means below 10% load, all bets are off. And as we have seen, there indeed are. So this model I have there in the breadboard can deliver up to 200 milliamps. It's a 1 watt type. So we need at least to pull out 20 milliamps to get into a region where that thing behaves like it should. be warned, not all of these converters allow you 0% load. Some of them don't like that and will quit their job. So with a load of 20 milliamps, things are looking better. Output voltage is now 5.19 volts. And but we're drawing about 45 milliamps. Just to remember you, when we had no load, we are already drawing about 20 milliamps. So, that's interesting. Let's see if we draw a little bit more current, what happens. So at 50 milliamps, 5.04 volts, and we're drawing 80 milliamps of current. At about, let's say 96 milliamps, we have 4.86 volts output. And we're drawing 135 milliamps. And near the advertised 200 milliamps, it's only 177. Our output voltage is down to 4.6 volts. And we're drawing, let's say 225. So I scribbled down the values we measured and, so our load 0, 20, 50, 96, 176. Our output voltage, 0 load, forget it, but 5.19, 505, 4.86, 4.61. The input current, increasing, of course. And if you calculate the efficiency of that thing, it looks bad. So at 20 milliamps, 46%, and then slowly rising up to 72%. I mean, even that, 70 or 80 cent per piece, including shipping, step-up converter from Banggood, I had a look at lately. Card link performed much better. Even in the output, the output voltage of that thing was rock stable, and but thing is, it works as advertised. So let's make some advertisement for the vendor of this impressive product, or not. So it's a Recom RFB series DC-DC converter type 0505. So from 5 volts to 5 volts, other variants available. You get them for about, $2 or $3 a piece from regular sources like DigiKey or so. So that's the efficiency curve advertised. Load 0 to 100%, or from 0 milliamps to 200 milliamps, and from 0 to 100% efficiency. And you see the thing peaks out officially at 80%. And let's say below 20% load, it goes down steeply. And remember, below 10% load, the thing is not really specified. So we started with our measurements at 20 milliamps, and we got 64% efficiency, which is okay. Then at 50 milliamps, 25% load, 63. Then here at 48%, 69, and at 88%, 176 milliamps, 27. So we're lagging about 8% behind the advertised curve. Nobody will sue them for that, I guess. I mean, it's their cheapest series. Of course, I bought the cheapest. But what you should keep in mind is that generally, even the more expensive ones, the efficiency of these things, especially in the low load area, is abhorrent. Okay, so yeah, at minimal advertised load below 50% efficiency. Yeah, keep that in mind when you design something that's run by batteries. The datasheet gives you also a nice graphic called tolerance envelope. And you see the load here from 10 to 100%. We have a typical load line, yeah, a V nominal. That line here, that should be 5 volts or 0%. Then we have a typical load line that descends from plus 5% to minus 2%. And then we have some lines which are, yeah, have no name, but they go from plus 10% at plus 5% maximum load, or, yeah, I guess 0% to minus 5%. But what we measured at 88% were 7.8% under nominal value. And at 96 milliamps, so about 50% load, we were at minus 2.8% nominal value. And yeah, 25% plus 1%, that would be inside this envelope. And at 20 milliamps, 10% load, we were actually at plus 3.8% of over 5 volts. So yeah, our line we measured looks more like that. And I guess we would end up here at, yeah, guesswork minus 10%. And yeah, you could say this is totally out of spec, but yeah, unfortunately, that's only yeah, a marketing graphic. You have to look up here. So first of all, we have an output accuracy. That is, well, where is our 5 volt line? Or do we get 5 volt out at all if we put 5 volt in? And that starts with minus 2% typical, but plus minus 5% maximum. So that's, yeah, your baseline. And then you have the load regulation between 10 and 100%. And that's plus minus 10% typical. Yeah, that's nowhere, that's not that typical load line here. Or plus minus 15% max. So what we measured is absolutely within the specifications, the numbers. Forget about these graphics when you find them in the data sheets for those things. Yeah, and in the beginning I mentioned these things are nothing else than transformers for, yeah, DC. And yeah, our specific thingy here on the board, its equivalent circuit would be a nice battery with 5.19 volts, yeah, starting at 10% load, and then a series resistor of, yeah, about-ish 3.7 ohms. So yeah, you get that line. You have to keep that in mind if you have varying loads on the output of the thing. Yeah? that can really ruin your day. If you say, okay, I buy that 5 volt, 5 volt, okay, maximum 200 milliamps. And yeah, some chips can take the minus 10%, so still run at 4.5 volts, but there are also chips out there who are specified only as plus minus 5% of 5 volt as operating range. Then going to 100% load here, yeah, ruins your day. What that also says is, yeah, you're between the devil and the deep blue sea. Yeah, to get a high efficiency, you should operate that thing in, yeah, on high load. But when you are operating it at high load, really near 100%, your output voltage is going down. Looking at the output ripple, so only AC coupled here, bandwidth limit 20 megahertz. Yeah, it doesn't look that nice, does it? At yeah, 170 milliamps output, and yeah, for some reason the thing went down to 4.485. Let's say 4.5 volts. So yeah, this is really borderline right now. Yeah, one unit is 50 millivolts, so 1, 2, 3, 4, 5, and there is a little grizzle that goes really down and really up. I don't know if you can see these really fine lines here. Yeah, that peak's going down and here's one going up. But yeah, if you really count them peak to peak, you have 150, yeah, worst case 200 millivolts ripple on the output. And even with a 100 nanofarad capacitor directly at the output, yeah, not really better. That's still 150 if you count in all the spikes, 200 millivolts output ripple. Let's see what the datasheet says about that. Well, the datasheet says output ripple and noise, typical 55 millivolts peak to peak, 100 millivolts peak to peak, max at 20 megahertz bandwidth. That's what I measured. And there is a note 4, and of course I read that in advance. So I put that 100 nanofarad MLCC, so multi-layer ceramic capacitor, across the output. And yeah, let's try that again with a little lower load, let's say 100 milliamps. And yeah, at approximately 100 milliamps, the output ripple is a little bit lower. Yeah, you could say that yeah, the bulk fits in 100 millivolts, but if you count in these sharp spikes here, we are still at yeah, in some cases, okay, let's say 150 millivolts. And with another little trick, things look even better. So yeah, now you could, yeah, it's not counting the spikes, it's well below 100 millivolts. So yeah, without counting the spikes. With the spikes, it's still, yeah, let's say 150. So, and the trick is I added, can you see that down there? Not only 100 nanofarad ceramic, but also a 10 microfarad electrolytic, that one at the input. And we need to, why I did that, or what gave me the idea, we have to have another look into the data sheet in a moment. But in all fairness to that thing, okay, you are drawing here at 100 kilohertz relatively high currents. And these things might perform better, or will definitely perform better, on a PCB that is designed, accordingly. In the datasheet, they have an extra page for EMC compliance. Meaning, we already have that output capacitor here of 100 nanofarad. And I added here that capacitor, which is needed for EMC compliance for about, I choose 10 microfarad. In class A, without the inductor and these capacitors here, which should be, depending on your application, of X or Y type, security capacitors. Just to keep compliant with class A, you need that capacitor here. Class A is for industrial environments, which allows for much higher emissions than class B, which is for household appliances and such. There you need the whole shebang. These capacitors here, the inductor, and that one I already had. Sorry. And you saw, obviously, they made their measurements about output ripple, assuming that you had here at the input some EMC filtering in place. Lots of assumptions here and optimizations. It's almost like, mileage per gallon measurements for cars, or liters per 100 kilometer in the rest of the world. And that EMC filtering is important because you have a huge reflected back ripple current. It's a switch mode power supply of 20 milliamps peak to peak. And that's depending on what you do. You say, I'm just fiddling around. I have no intentions to certify that for class A or class B. But anyway, that 20 milliamps back ripple here on your positive supply and mirrored down on your ground line or your ground plane, that can ruin your application, or at least if you have not only digital but also analog stuff on here, let's say a precision amplifier or something, you don't want to have that noise. You should at least put that 10 microfarad capacitor in here. Maybe a little inductor. I mean, it doesn't cost much, and And these were all the pitfalls surrounding the unregulated, isolated DC-DC converters that came at least to my mind. These are dirt cheap. I mean, I think I mentioned it before, $2 or so, or maybe $3 on regular sources like DigiKey, Mouser, whatever. But there are no magic bullets. They do have serious limitations. If you don't look out for these limitations, your design simply won't work. If you expect 5.00 volts out of these things, if you put 5.00 volts in, yeah, you already lost. And yeah, noisy as hell. What else? Bad efficiency, especially if you drive them at the low end of their maximum load, and yeah, really low voltage output if you drive them at the high end of towards their maximum load. So yeah, but a nice little building block to get, cheap building block to get a completely galvanically isolated second power rail. Bye.